Today we'll be giving a talk about PCA, Principal Component Analysis, and overall summarization. And overall on PCA is one of the most important techniques for dimensionality reduction. Its purpose is to take a large table of data and reduce the number of columns, or as known as dimensions, to create a smaller, simpler dataset while keeping as much as the information as possible. This process is visualized as finding the optimal angle to take a picture of the data, specifically the projection that leaves the data points as spaced out as possible. So looking at the picture, we can see that there are many angles that you can capture, but some angles may capture very less of people, but some angles may capture a lot, various number of people. And PCA is just like using a camera and choose the best angle to take a shot, and the same is applied with the data points in the plot. So we have scattered data points here, and these lines represent the angle to take a shot. If you take a shot from this angle, the data that you will receive will not be vary so much, so there is very less of information you will receive. But if you take an angle like this, you can see that it is much more varied here, and you will retain a lot of information. That is the idea and purpose of PCA. And the idea of reducing dimensionality, and for example, we are choosing a house, and here are its properties. We are considering to choose a house. A house has many properties. It has its size, number of rooms, number of bathrooms, the number of schools around the location, the number of the index of crime rate. And here we only demonstrate 5 features. So 5 features are a little bit not so much, right? But if there are like 1,000 features, how can we evaluate this piece of data the most efficient way? It's using PCA. PCA will divide these 1,000 features into a much smaller number of features. We group them. For example, we will group these similar features into size feature, and we will group school around and crime rate into location feature, and they will find the most efficient way to keep as much as possible, as much information as possible. Get the idea? So this is a visual representation of 2 dimensions. The size is the number of rooms. This axis represents the number of rooms, and the axis that is perpendicular to this axis, to that axis, is the number of rooms. So we kind of project these points onto this slide right here, and we will get the 1-dimension representation of that exact piece of data. We project and we get 1 dimension. We call it size feature. A caveat here is that using PCA won't discard all the features, but rather they create new features uncorrelated to the original features. So we don't delete size, number of rooms, or number of bathrooms, but rather size feature is a linear combination of these things right here. Like that linear combination. Remember that? Here. I got this. Here in the housing example at the beginning of the note, the size feature can be 0.9 multiplied with size plus 0.8 multiplied with number of rooms, 0.2 multiply with the number of bedrooms. Because the size is the biggest factor that makes up the size feature, and therefore we can say that size feature is kind of an approximate representation of size. You know, that's how we decide the meaning of a PC. We'll go on to the foundational concept of that makes up the PCA. But before that, we will try to summarize what we have been talking, we have been discussing. So PCA is just like you take a very large piece of data here and you reduce its complexity by creating new criteria to evaluate those pieces of data. Like we'll group the original features into a bigger, more general feature like this, and we will retain as much as possible the number of information, the amount of information. That's the whole idea behind PCA. So the first thing we'll go into is mean and variance. Mean is the average of a set of numbers. It represents point of equilibrium on the balance for a set. So here I have an example. You can see that we are trying to balance the weight on a stick like this. So which point will be the point of equilibrium, and how can we find that point? The number here represents the distance from the weight to the wall. As I have said, the mean is the point of equilibrium, so we will add all the distances together and we will define by the number of weights. So that means we will add 1 plus 2 plus 6 divided by 3. We get 3. So at the distance to the wall of 3, the weight will be all balanced. Variance measures how spread out a set is calculated by taking the average of squares of the distances from each point to the center. In this case is mean. For two-dimensional data, one can calculate the x variance spread horizontally and the y variance spread vertically. So here is our mean, and we will have the weights arranged and put and line up side by side with the mean weight right here. We'll calculate the distance from each weight to the mean, and then we will square them up. The point of squaring them up is for them to not cancel out each other, you know, like -1, -1 plus +1 will equal 0, so they will cancel them out, and that is nonsense. So we will just square them up, then we'll divide by the number of weights. We'll get the variance, and you can see that the variance on these weights compared to the variance of these weights are different. The variance of these weights are bigger than the variance right here because they are more spread out. So that is what it means to say that variance measures how much spread out is a set from its mean. But variance can only be applied to one variable. So how can we tell the difference between these two plots right here? You can see that the variance on whatever axis, the x-axis or the y-axis, is equal. Okay. 2 plus 2 divided by 3, 2 plus 2 divided by 3, 1 plus 1, this by the y-axis, 1 plus 1 divided by 3 and 1 plus 1 divided by 3. How can we tell the difference when they are fundamentally very different right here? How can we tell that these two are different if we only base on variance? So we have to bring in the third metric. The third metric is covariance. Covariance will help distinguish between datasets that might have the same x and y variances but are fundamentally different in structure. You can see this piece of data right here is going down. This piece of data right here have the intention to go up. They are different. It will quantify the trend of a piece of data and evaluate how much or to what extent the variables change together. So our ancestors come up with an idea is that they will calculate the average of the sum of products of coordinates after they centering the data. So here's how we interpret a covariance value. So if it is a positive covariance, that means that as x value increases, the y value also increases. You know that the whole plot will look like it is charging forward. You know, it forms a forward diagonal line. The negative value mean that the whole piece of data is going down. Positive means going up. Here are some more cases. If we add more points, it will look like this: negative covariance, because as x direction value, as x direction grows, y direction goes down. As x direction go to the right, the y direction remains stable. What do I mean by stable? You know that the y values of all these points are kind of very symmetric, are very centered, you know. So they do not have a specific trend of going anywhere. They just stay in the center. For positive covariance, it means that as x direction goes to the right, the y direction will go up. So that is this what it means by saying the covariance of a piece of data is 0. You can see that data is like, say, in the center instead of having any specific trend. But covariance and variance alone, you cannot use them in assessing a piece of data without organizing them into a matrix, and that is what we call a covariance matrix. The statistics of the data are summarized into the covariance matrix, and that's what I have been explaining for a 2D dataset. This is a 2 multiplied to 2x2 matrix. So on the diagonal entries, it contains the variances, and the off diagonal entries contain the covariance, and the covariance of x to y is equal to the covariance of y to x. They are all the same value. The crucial property of covariance matrices is that they are always symmetric, meaning that the entries on the top right and the bottom left are the same. So right here you can see the variance. Let me just zoom it out. Easier to explain. The variance of x is 9 because on the by looking at the x-axis you can already tell why the value is so high, because the piece of data is more spread out on the x-axis and it is less spread out on the y-axis. You know, if we just project all these points onto the y-axis, you can see that they are kind of clustered up together. They are not spread out like on the x-axis, and the covariance of x to y is 4, which is a positive number. It means that the piece of data is going up. That is how you interpret covariance matrix. Okay, we can come up to a harder part: the eigenvalues, eigenvectors, and linear transformation. The covariance matrix can be treated as a linear transformation that stretches the data space. This is where eigenvalues and eigenvectors come in. So, eigenvectors are the directions of our data. This vector points into the direction that is most spread out. You know, like define the spectrum. They give the direction of the stretching. So, for example, let me just talk over the eigenvalues. The eigenvalues indicate the magnitudes of that stretch out in that direction. The direction is indicated by eigenvectors. The magnitude is indicated by eigenvalues. These values represent the scaling factor or the magnitude of the stretching. Because covariance matrices are symmetric, then their eigenvectors are always perpendicular to each other, and the eigenvalues will be real numbers. So here it is. So here you can see that we have calculated the eigenvectors for whatever piece of data here is, 2, 1 and minus 1, 2. So by looking at these eigenvectors, you can see the no, let me talk it over again. We are talking about linear transformations. So we have here, this is a covariance matrix. A covariance matrix will describe how to turn a random piece of data, or how to turn any piece of data into another piece of data that has the shape of this covariance matrix. What I mean is, if you linearly transform this piece of data by using the covariance matrix, the covariance matrix will provide the information like how stretched out you should be on the x-axis, how stretched out you should be on the y-axis. It will provide the information for your current piece of data and turns it into another piece of data that has the properties described by the covariance matrix. So here you can see that if we update the coordinates of the I hat vector to from 10 if I'm not mistaken to 94, the j hat from 01 to 43. It means that we are performing a linear transformation, and it will trick this circle out into an ellipse. and the eigenvectors determine that in which direction will this circle be stretched, and the eigenvalues determine the intensity of that stretching. uh, 11 to 1, 11 means more stretching, and 1 means less stretching. You can see. Let me talk it in a more concise way. So let's go back into the covariance matrix. The covariance matrix contains, I will type it right here, covariance matrix contains the information about the shape of a piece of data. If you apply the linear transformation through on any matrix or any piece of data, through the covariance matrix, it will transform that matrix into a new matrix that has the same shape as our piece of data. Okay. Okay. I hope you have understood by now. That's the essence of linear transformation. We'll go down to loadings and scores. Loadings and scores. Loading is simply the coefficients of the linear combination that forms a PC, and it provides a way to understand the PC. We have explained just on the surface level of on the surface. We have explained loading on the surface level at the beginning of our talk, so I go and repeat it here. How you can calculate loading, and here is the linear combination right here. The linear combination is right here. You can see the 0.9 indicates a very high correlation with the a very high correlation of the PC with the original data. So that means this PC1 is very close to this PC X1, and is 3 times closer to this X1 to compared to this X2 right here. So the loading scores, how we would describe the linear combination on a plot. So minus 0.242, which means that we will go 2.2 unit, 0.242 unit to the left, and then we will go up by 0.97 to the upward direction. Okay, 2.2, 242 to the left, and 0.97 upwards. Yeah, here. Okay, that's how we construct PC2 from the two genes, gene 1 and gene 2, and that is also the definition of linear combination. What is a formula to calculate loading score. Loading score is calculated by multiplying the eigenvector coefficient, which simply means the coordinate of the eigenvector with the square root of its eigenvalue. Here. Okay. The loading score, the closer the loading score is to 1, the higher the compatible cái gì? Độ tương thích này. Okay. So the higher the độ tương thích, the closer the loading score is to the -1, the less it will be similar to the less the PC will be similar to the original features. The score is basically the coordinates of a point in a new coordinate system. It's a change of basis transformation. Okay, get it? I think you get it. An eigenvalue is actually variation, and variation is a metric that measures variation. So here we have calculate the sum of the square distances for PC1, and we'll divide it by the number of data points -1. So this is just like the formula to calculate variance. Don't you remember? We'll here. Yeah, it's the same thing. So we can say that eigenvalue is the same as variation. Okay, read it for yourself. And because it is the same as variation, we can use eigenvalues to calculate how much information that we have lost. So for the sake of the example, imagine that the variation for PC1 is 15 and the variation for PC2 is 3. That means that the total variation around both PCs is 15 plus 3 equal 18, and that means that PC1 accounts for 83% of the total variation around the PCs. That means that by looking at PC1, we can describe 83% of the original data. You can see that the PC1, the data on the PC1 is much more spread out. The data on the PC2, by projecting this point onto the axis. PC2 accounts for 17%, and the script plot is there for us to visualize these values by bringing them onto the bar graph. Yeah, I have just described about how we can calculate the error of PCA by adding all the variation of our PCs and use one minus some, and we will get the error. Okay, so yeah, just some complex formulas. Won't get too deep. You can read it for yourself. One more thing I want to say before we go into the PCA procedure. I want to say about why I will write why do we want to find the axis, the direction that is most varied? No, that describes our data best, and also the direction that our data is most varied to that direction, which means that you can also interpret this way that the direction that is most varied in data equal the direction that describes our data best. Here, it's a strange thing. How can the direction and to that direction our data is varied the most? It's the same thing as the direction, and to that direction our data can be described best. How do these two concepts resemble each other? So here, imagining that the housing right here, the housing data right here. If we have another, if we describe the house by this feature, by the if we describe each house by the number of material, if we describe each house by the number of material, it would be such a bad idea, because every house is built by brick, right? It's built by brick, so like a very large number of samples will have the same data. If we describe the house by the number of materials, when every house is built by brick, it's just a fantasy, but just assume that every house is built by brick, the samples will have the same data. It will be sample 1 brick, sample 2 brick, sample 3 brick. Yeah, and that is what I mean by the data will be less varied when you choose the wrong PC. Okay, but what if we describe a house by the size? Not every house will have the same size, so we will have more variation, and which means we will have more information if we describe a house by size. And so that does answer our question, how is the direction that our data is varied the most resembles, is equivalent to the direction that our data will be best described. The more variation we have, which means the more data. What do I mean by the more data? Like a dormitory will have be bigger than a normal house, right? Dormitory bigger than a normal house, and a house of 8 people will be bigger than the house of 4 people. So that means we can describe more more data by only the size feature. So that is what I mean. More variation, the more information will equal the more information. Okay. Okay. Hope you get the idea. I will make a separate note on this topic. Not a separate note, but I will add some notes on this topic later on. I will go into the main meal PCA procedure. First, we're centering the data, moving it to the center. Yeah, moving it to the center. This, what I mean by moving it to the center here. Originally, our data will sit somewhere on here, right? It will sit somewhere on here, and we will center it by subtracting the mean by x-axis and the mean by y-axis to every single data point in this, and they will be automatically centered. Okay. Here, the origin of our plot is the mean value. The mean value is here. Okay. The second thing is calculating the covariance matrix. We have said about this before. Covariance matrix describes the shape of our data. Then we were extracting the eigenstuff from that covariance matrix. The eigenvectors, which are our directions, the corresponding eigenvalues, which are the magnitudes. Here. And here is also a visual, not quite accurate, but visual representation of the eigenvalues. Here, right here, for a 5D table of data. Yeah, our eigenvalues, and then we will ordering the eigenvalues. We're sorting it from big to small, and also sorting their corresponding eigenvectors. Because from big to small, small to big is the same, and which eigenvector has the biggest eigenvalue will carry the most amount of information. We have discussed about this. Eigenvalue equal variation. So we'll choose k numbers of eigenvectors based on their the size, the big of an eigenvalue. Choose, and then we will project all these data points onto our new coordinate system created by the eigenvectors. If we choose 2 eigenvectors, we'll get a 2D plot, a 2D representation of our original 5D table of data. We'll project them, and from this to this, we have performed a change of basis. From this to this, and then we can interpret our new pieces by looking at the loading. I have talked about this. The loading are the coefficients of our linear combination. Here, 0.97 part of gene 2 means a very high compatibility. If I'm not mistaken, it's pronounced like that. 0.97 is closer to 1, so it means that we can describe the PC2 by just only the Gen2, and we don't even care about the Gen1 because it is not close to -1. It is further to -1 than the Gen2 2 plus 1. Okay, and we can name the W1, the W2 like we name the size feature and the location feature on the beginning example of housing data, and location feature, size feature, W1, W2. We create a smaller table but retains the most amount of information as possible, as much information as possible. That's an overview on PCA. I will walk through the code. We have a piece of code right here. Yeah, that's all.